Okay, this is 2-4, biconditional statements and definitions. When you combine a conditional statement and its converse, you create what we call a biconditional statement. A biconditional statement is a statement that can be written in the form P if and only if Q. That means if P then Q, and it also means if Q then P. So it's a reversible condition. It asks us to write the conditional statement and converse within each biconditional. So we're given two angles are congruent if and only if their measures are equal. So let's first identify our hypothesis and our conclusion. Our hypothesis, if we're going from left to right, would be two angles are congruent. And our conclusion would be their measures are equal. Okay, so when we're writing our conditional, remember it's if our hypothesis, then our conclusion. And when we write our converse, we flip our hypothesis and our conclusion there. Okay, you guys see if you can write the conditional and the converse on your own. Okay, pause this video. Alrighty, hopefully you've got something like this. So our conditional should say if two angles are congruent, then their measures are equal. And our converse should say the opposite. If their measures are equal, then the two angles are congruent. Okay, we're going to skip B for now and do that one in class together. All right, for a biconditional statement to be true, both the conditional statement and its converse must be true. If either of those, the conditional or the converse, are false, then the biconditional statement is false. In geometry, biconditional statements are used to write definitions, and a definition is a statement that describes a mathematical object and can be written as a true biconditional. In our glossary, a polygon is defined as a closed plane figure formed by three or more line segments. We have some examples of polygons and non-polygons here. So our polygons, if you notice, all have straight line segments. Over here in our non-polygon example, do we see this curve? That's what makes that example not a polygon. Our polygons all have side lengths that are connected end to end. So here we have what looks to be almost a triangle, but because we have that opening there, that does not work. We've got something here that looks like a triangle with a little extra tail. This is not a polygon because of that extra tail. And then we've got something here that since we have two crisscrossing side lengths here, that is not a polygon either. And then the closed plane figure part of that means that it needs to be a 2D shape. So we cannot have our box here. That is not a polygon. Okay, a couple more definitions. A triangle is defined as a three-sided polygon. And a quadrilateral is a four-sided polygon. Okay, our last example here should be pretty quick. It says write each definition as a biconditional. A pentagon is a five-sided polygon. So you'd say a polygon is a pentagon if and only if it has five sides. I think that should be an S. Five sides. Okay, B says a right angle measures 90 degrees. We would say an angle is a right angle if and only if it measures 90 degrees. All right, we'll do more practice with those in class tomorrow. Have a good night, y'all.